Okay, now we can talk about electromagnets because we have dwelt into solenoids. Now, solenoids, because you know that running a current through solenoid, it can produce a magnetic effect, and it can be made strong. Okay, you can strengthen it by doing three things: placing iron core, passing a big current, and increasing the number of coils. By doing so, we can make a strong electromagnet. Okay, now, so what's the good thing about having an electromagnet? What we want it is that it is able to lose its magnetism quickly once the current stops flowing through it. So we can actually switch on and switch off the magnet. That's a good thing about electromagnet. So you can see here the positive advantages. You can switch it on and off. You can make it stronger or weaker. And the last one, you can reverse the polarity of the electromagnet. How do you reverse the polarity? You reverse the direction of current. So this is something good that you can play around with electromagnets. Okay, some of the devices that uses it is your circuit breaker, magnetic relay, and electric bell. Let us look at the electric bell more carefully. Okay, now, how does it work? Okay, we generally tend to start from somewhere. Obviously, the best place to start here is the switch. Okay, it's the switch. So what happens here? Okay, let's start from the switch. You switch it on. So this is the first part. Okay, circuit is complete. The current flow. Okay, first part we talk about current flowing. In this case, we use a logical sequence to try to answer this question. How does your electric bell works? So when your switch is on, current is flowing. Okay, current flows. Okay, now what's going to happen is that when the current flows through this electromagnet, okay, so flowing through here, okay, using your right hand grip rule, you realize that what we're going to get, okay, is when we're going to cause the electromagnet to become magnetized. Okay, obviously when the electromagnet become magnetized, what happened? You can see this is a soft iron. And because this is iron here, what's going to happen? It will attract. So this is 2A, where the current will flow. Okay, sorry, let me erase this. Okay, 2A, we talk about the current flowing. Then the second part, we talk about the iron armature being attracted, okay, to the iron steel. Now, obviously when it's attracted, what happens? The hammer will hit the gong. So this is the stage 3. When the soft iron armature is attracted, the hammer will hit the gong. And this produces a sound. Now, what happens here when the armature moves in is that, oh no, the circuit will be broken at the contact screw because the whole iron armature moves forward. Okay, the whole armature moves forward. So what's going to happen is there's going to be a disconnection at this point. And when there's a disconnection, what's going to happen? We said the circuit is broken and the current stops flowing. So the electromagnet loses the magnetism. Now, what happens when the electromagnet loses its magnetism? Will the soft iron armature still be attracted here? Answer is no. So when the electromagnet loses its magnetism, how does the iron armature move back? It's the spring that pulls the iron armature back. So it makes the contact screw, completing the circuit again. So as you press onto the switch, the cycle will keep repeating. A cycle will keep repeating. So it will be hitting the gong. Ding, 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 ding. That's how it works. Okay, that's how it works. So electric bell is an interesting device that uses an electromagnet in a good way. Okay, so do study this electric bell because it talks about how they use electricity and magnetism to create a device or an application of it. Next one, which is the last one, we talk about the forces on current carrying conductors. Okay, this is actually called the kicking wire experiment. Okay, they call it the kicking wire experiment. Again, you can go online to check it out. Okay, I will not say too much about this. But what I need you to know is this, is that this thing called the Fleming's left hand rule. Okay, please arrange your left hand. This must be a left hand. Oh, ugly. This must be a left hand. Okay, and then you must have your fingers all placed 90 degrees around one another. Okay, 90 degrees. I always remember it as motion. I generally call it force, which I call it father. Okay, father. The field, okay, is what kind of field? It's actually a magnetic field. So I'll call this the mother. And the last one is the current. So obviously this is the child. Father, mother, child. Okay, do the setup and remember father, mother, child. How do you use the Fleming's left hand rule? What you do is you need to align it carefully. Okay, first you must always know where the direction. So always in diagrams like this, check out flow of current. Okay, next you must know what is the magnetic field direction. With these two, you can determine the force. Okay, so take note, this is the explanation of it. How does the current interact with the magnetic field? So your current carrying wire actually has a magnetic field, which we have discussed about it earlier. So when you place the wire in another magnetic field, they will interact. And obviously magnetic field when they interact is only two things. One is repulsion, one is attraction. And these two are magnetic force. So this force experience is actually a magnetic force. Okay? The force experience is a magnetic force. And how can the force be greater? We can either increase the current or we can use a stronger magnetic field. Okay, so this is what we call the kicking wire experiment. Okay, what does it do? It tells us that a carrying conducting wire can interact with a magnet, okay, to produce a force. I say again, a current carrying wire can interact with a magnetic field to cause a force. In actual fact, in the diagram, okay, the current flows in this direction, okay, green arrow. Okay, my magnetic field is always from north to south. Okay, so you can see. So with these two here, you can align your fingers. Okay, take note. Blue is for your magnetic field, which is also your index finger. Okay, then the green is for your current, and this is for your middle finger. So with this, and if you try to align, okay, the current is facing into the paper. This is into the paper. Is specifically to this diagram, it's actually into the paper. Magnetic field is from down to up. Okay, current going to inside the paper, magnetic field going upwards. You realize your thumb is pointing to the right. Your thumb is moving to the, your thumb points to the right. And obviously if your palm points to the right, what does it mean? It means that the force experienced by the wire is to the right. So what will be the motion? It will move towards the right. Okay, so now next one. Okay, let's try this one. Let's take the direction of motion of a positively charged particle as they enter a magnetic field. So assuming I got magnetic field that goes like this. Okay, my magnetic field. Okay, this is the south pole, this is the north pole. Okay, north pole magnet is, sorry, my bad. Draw wrongly. This is not north pole, this is, let me redraw this whole thing over here. So south pole, north pole, so my magnetic field looks like this. Okay, now this is my magnetic field, so my green equals to magnetic field. Okay, next up we're gonna have our charge, okay, our current, a positive charge flowing in this direction, positive charge. Now this is actually testing your concept here. A flowing positive charge, or you can say the moving positive charge. A moving positive charge is actually your current. So we are saying is that current is flowing from left to right. So what you do is you take your middle finger and point towards the right. Your magnetic field will align it to the top. So how will your positive charge move? Your positive charge will move out of the paper. Okay, because once you do the alignment, you realize, oh, the thumb is pointing towards you. So if it's pointing towards you, it is actually out of the paper. Okay, so just take note of this. Now, the other one we talk about is a negative charge. Okay, negative charge. So this is a bit trickier. So let's use the same example as I've drawn just now. South here, north here. Okay, the magnetic field obviously is this way. Okay, then I have my, now use another different color. Say this is my negative charge. Now, how will the negative charge flow? It will flow in this direction. But remember, when we say current, remember we are talking about current. Current equals flow of positive charge. So if my negative charge goes in this direction, how will my current be like? My current will actually be in this direction. Okay, orange equals to current. So my current will actually be in the opposite direction. So now let's change the position. The middle finger point towards the left. Your magnetic field point upwards. You realize your thumb is pointing down. So what will your negative charge experience? So your negative charge will move into the paper. Okay, go and try it out. Question 3 and question 4. These two are important. You must be sure that you are able to do it. Okay, this is actually a very simple basic of your Fleming's left-hand rule. You must know how to use it properly. Okay, so this marks the end for the electromagnetism. We talk about the right-hand grip rule, the left-hand grip rule, and how we can use Fleming's left-hand rule to find out motion.